All right, so the logistic differential equation, just like the differential equations for exponentials that we looked at earlier, the logistic is very similar. It starts with a rate of change. This is the rate of change of population over time. We've got a constant. We've got a P for population. We've got an M for a maximum population or a carrying capacity for population. And so we just can combine this logistic function into some smaller parts. And when we differentiate it, it's going to turn into something where we're going to have to use the partial fractions. All right. So what is the carrying capacity? So we've got this problem, right? We're investigating population. So the growth rate of a population of bears in a newly established wildlife preserve is modeled by the differential equation dp dt equals 0.008 p minus 100 p, where t is measured in years. So what is the carrying capacity for bears in this preserve? That's the M part. That's the M part. So what is the carrying capacity for bears in this preserve? 100 bears. Okay. When we reach 100 bears, we've reached our full amount of sustainable population. What is the bear population when the population is growing fastest? Well, when the population is growing fastest, that's when you're at your halfway point on a logistic function. So we would say 50 bears. Anytime you're interested in when a population is growing fastest, that's going to be the exact halfway point between the exact halfway point for your carrying capacity. Okay. What is the rate of change of the population when it's growing fastest? Remember, this is rate of change. This is rate of change. So if I want to know what's the rate of change when it's growing fastest, well, I know that my population then would be 50. So I'd have 0.008 times 50 times 100 minus 50. So I'll need to punch that into my calculator here. Ugh. Ugh. And what is the rate of change when its population is growing fastest? And I got 20 bears per year. You're going to get 20 on this, but think about what you're talking about. You're talking about population of bears over a set piece of time, which in this case would be years. Okay? So this is a simpler logistic differential equation. Remember, we can actually integrate this and do some really neat things with it, and that's actually the next step.